Myself, Mr. Mothika Srinivas. I'm working as an assistant professor in Department of Chemistry of Sundarao Swanke Mahavidyalaya. This college is located in Mazalgaon, Peet District, Maharashtra State, India. In the first part of the video, we have discussed certain points from the gaseous state, like postulates of kinetic theory of gases, kinetic gas equation. We have deduced gas laws like Boyle's law, Charles' law, Graham's law of diffusion, Avogadro's hypothesis. In this part of the video, we'll discuss about the deviations from ideal behavior, van der Waals equation of state, critical phenomena, pressure-volume isotherm of real gases. The first point that we are going to discuss is the equation of state or ideal gas equation. So the deviation from ideal behavior of the gases. It is found that the real gases, they do not follow strictly this ideal gas equation. Or in other terms, we can say that this ideal gas equation PV is equal to nRT, which is derived from the postulates of the kinetic theory, is valid only for the ideal gas. Real gases obey this equation only approximately, and that too under conditions of low pressure and high temperature. The higher the pressure and lower the temperature, the greater are the deviations from the ideal behavior. So we have to see exactly what happens at high pressure and low temperature. It is to be noted that certain gases like carbon dioxide, sulfur dioxide and ammonia show much larger deviations than other gases like hydrogen, oxygen, nitrogen, etc. Now we will discuss the two postulates that are not followed by the gases at high pressure and low temperature. The first postulate which is not followed is the volume occupied by the molecules themselves is negligibly small as compared to the total volume occupied by the gas. Let us see. Here in this diagram, we have considered two situations. One is ideal, the second one is real. When the pressure is low or the temperature is high, in that case, the gases they follow this kinetic gas equation and as well as PV is equal to nRT ideal gas equation. And the gases behave ideally. But if the pressure is high, the gases they do not follow the postulate of kinetic theory of gases. Now you can see here in this picture, when the pressure is very high, the total volume which was much more, now it becomes very less. So therefore, the actual volume occupied by single gas molecule, now it is not negligible as compared to the total volume of gas. Alternatively, we can say that the actual volume occupied by single gas molecule is now significant as compared to the total volume of the gas. This is the complete violation of postulate of kinetic theory of gases. The same is the case when the temperature is lowered. When the temperature is lowered, the gas molecules, their kinetic energies, they become less and less. The molecules, they come close and close together. And when the molecules, they come very close together, the total volume becomes less. And therefore, the molecules, they attain the same condition as shown here. Again, the actual volume occupied by single gas molecule, again it becomes significant as compared to the total volume of gas. So we have seen here, when the pressure is high or when the temperature is low, in both cases, the gases, they do not obey, they do not follow the postulate of the kinetic theory of gases. So the second postulate which is not followed is the forces of attraction between gas molecules are negligible. So this assumption is valid at low pressures or at high temperatures, as you can see in this figure. But at high pressure and low temperature, this postulate is not followed. It can be seen here that at high temperature and low pressure, The gas molecules lie far apart from one another, but at high pressure or at low temperature, the situation is different than the previous one. You can see here, at high pressure or at low temperature, the volume is small and molecules lie closer to one another. The intermolecular forces of attraction, they are shown here in this figure, are appreciable and they cannot be ignored. Hence, the postulate 2 does not hold under conditions of high pressure and low temperature. It is necessary therefore to apply suitable corrections to the ideal gas equation so as to make it applicable to real gases. In 1873, J.D. van der Waals proposed his famous equation of state for a non-ideal, that is, imperfect gas. He modified the ideal gas equation PV is equal to nRT so that it can be used for the real gases. He said that the gas molecules, they are not mass points, but they behave like rigid spheres and they are having certain diameter. That there exist intermolecular forces of attraction between them. The two corrections that he did, or the van der Waals equation corrects for two properties of real gases, the excluded volume of a gas particle and the attractive forces between gas molecules. Now we will see here correction due to volume of gas molecule. The ideal gas equation PV is equal to nRT is derived on the assumption that the gas molecules are mass points. That is, they do not have finite volume. But van der Waals has abandoned this assumption and suggested that a correction term NB should be subtracted from the total volume V in order to get the ideal volume which is compressible. In order to understand the meaning of the correction term NB, let us consider two gas molecules which are unpenetrable and incompressible. So you can see here two spheres which are unpenetrable and incompressible. It can be seen here that the centers of the two spheres, they cannot come closer than the distance d. So for this pair of molecules, we have to consider this dotted sphere of radius d, and therefore volume of this dotted sphere is 4 by 3 pi g cube. So this is called the excluded volume for two molecules. Now the excluded volume for two molecules, when it is 4 by 3 pi d cube, we have to consider the excluded volume for single molecule. So it can be divided by 2. When it is divided by 2, the excluded volume per molecule will be equal to 2 by 3 pi d cube. Now we will calculate the actual volume of one gas molecule, and this one gas molecule has the radius r. So by using formula 4 by 3 pi r cube. So this r is equal to d by 2. So the equation becomes 4 by 3 pi d by 2 cube. So this is equal to 1 by 6 pi d cube. So the excluded volume per molecule, which we have seen in the previous slide, was 2 by 3 pi d cube. And you can see here it is 4 times to that of the 1 by 6 pi d cube, means 4 times to the actual volume of the gas molecule. So the excluded volume per mole of the gas, it can be given. This is equal to Na, this is Avogadro's number, multiplied by 2 by 3 pi d cube, or instead of 2 by 3 pi d cube, we can write 4 into 1 by 6 pi d cube. So all this is equal to B. Thus the compressible volume per mole of the gas, it would be equal to V minus B. And instead of 1 mole, when we consider n number of moles, then the equation becomes this is equal to V minus NB. Hence the ideal volume which is compressible is equal to V and B. Now we will see correction due to intermolecular forces of attraction. In the derivation of the ideal gas equation, it was considered, it was assumed that there are no intermolecular forces of attraction. But actually it is not so. In order to take into account the effect of intermolecular force of attraction, let us consider this figure. In this figure, there are certain molecules which are in the middle of the vessel. They are shown by green squares. Their behavior will be different than this another molecule which is shown by red square. This molecule is near the wall of the vessel. As it is seen here, the green space or these molecules, when they are at the middle of the vessel, they will be equally attracted by other molecules which are around it. Since these molecules, they are uniformly attracted on all sides by the neighboring molecule, their forces neutralize one another and there is no resultant attractive force. On the other hand, the molecule when approaches near the wall of the vessel, we mean this red sphere, it experiences attractive forces from the bulk of the molecules behind it. Hence, it will strike the wall of the vessel with a lower force and with a lower velocity, and therefore it will exert a lower pressure than it would have done if there were no forces of attraction because of these molecules behind it. It is therefore necessary to add a certain quantity to the pressure of the gas in order to get the ideal pressure. So the correct pressure would be capital P, and in that small p is added. So now we will see what is this small p which is added. So we will see here what exactly this small p is. The force of attraction exerted on a single gas molecule which is about to strike the wall of the vessel, it will evidently depend on the number of molecules per unit volume in the bulk of the gas. That it depends directly upon the density of the gas. Further, the number of molecules striking the wall at any given instant also depend directly upon the density of the gas. Thus, the total inward attractive pull, which gives a measure of the correction factor small p, is proportional to the square of the density of the gas, which is shown here by this equation 1. So this small p is proportional to square of the density of the gas. So this density is inversely proportional to volume. So therefore this rho square is inversely proportional to volume square. Thus the value of rho square for 1 mole of gas will be inversely proportional to the square of the volume, which is shown here by this equation 2. Here in this equation, this A is constant and it depends on the nature of the gas. Therefore, the ideal gas equation for 1 mole of gas takes the form which is shown here by this equation 3. Small p plus A by B square m multiplied by Vm minus B is equal to RT. Here, this Vm stands for molar volume of the gas. So this is known as van der Waals equation. The constants A and B, also known as van der Waals constants. So the van der Waals equation for n mole of gas is shown here. This van der Waals equation has lot of significance since the ideal gas equation PV is equal to nRT is modified so as to make it suitable for the real gases. Now we will discuss the point critical phenomena and pressure volume isotherms of carbon dioxide. The critical temperature of a gas can be defined as the temperature above which it cannot be liquefied, however high the pressure may be. Now we can see here, when the gases they are heated, they undergo expansion. But the same gas at the same temperature, when the pressure is increased or they are compressed at high pressure, the volume will decrease and they will attain a condition the gas will be liquefied by keep at the same temperature. Now again, if we increase the temperature, again the gas will undergo expansion. So the next temperature is higher. Therefore, so as to liquefy the same gas, we have to increase the pressure to more quantity. When the pressure is increased again, the gases they are liquefied. But now, here in this case, the pressure which is to be applied to liquefy the gas is higher than the previous one as the temperature is raised. Now, if we keep on raising the temperature, we have to keep on increasing the pressure so as to liquefy the gas. But this cannot be continued because this gas attains a certain temperature above which it cannot be liquefied, howsoever high its pressure is. For instance, the critical temperature of carbon dioxide is 31.1 degrees Celsius. This means that it is not possible to liquefy carbon dioxide beyond 31.1 degrees Celsius by any means. At the critical temperature, a certain pressure is needed to liquefy the gas. This pressure is called critical pressure. For example, at 31.1 degrees Celsius, carbon dioxide can be liquefied under a pressure of 72.9 atmosphere. The critical pressure of carbon dioxide gas is 72.9 atmosphere. So we can see here a series of isotherms. The importance of critical temperature of a gas was first discovered by T. Andrews in his experiments on pressure-volume relationships, or isotherms of carbon dioxide gas at a series of temperatures. The isotherms of carbon dioxide determined by him at different temperatures are shown here in this figure. Now we will consider the first isotherm at the lowest temperature, that is 13.1 or 13 degrees Celsius. The point A represents carbon dioxide in the gaseous state, occupying a certain volume under a certain pressure. On increasing the pressure, its volume diminishes as is indicated by the curve AB. So when we reach to point B, which represents a pressure of 49.8 atmosphere, liquefaction of the gas commences and therefore a rapid decrease from B to C takes place at the same pressure as more and more of the gas is converted into the liquid state. At C, the gas has been completely liquefied. Now, as the liquid is only slightly compressible, further increase of pressure produces only a small decrease of volume when we move from the point C to the point D. This is shown by a steep line CD, which is almost vertical. Thus, along the curve AB, carbon dioxide exists as gas. Along the curve BC, it exists partly as gas and partly as liquid, while along CD, it entirely exists as liquid. It may also be noted that considerable decrease of volume represented by BC takes place when the gas changes into the liquid state at a constant pressure. Or the second isotherm at 21 degrees Celsius shows similar behavior, except that now liquefaction will start at higher pressure and the horizontal portion, which was BC in the previous case, the second isotherm A1, B1, C1, D1 at 21.5 degrees Celsius temperature shows a similar behavior, except that now the liquefaction starts at a higher pressure and the horizontal portion B1 to C1 representing decrease in volume becomes smaller as compared to the previous horizontal portion BC. At still higher temperatures, the horizontal portion of the curve becomes shorter and shorter until it reaches a point represented by the temperature 31 degrees Celsius. By the point P, called as critical point, it reduces just to a single point. At this temperature, therefore, the gas passes into liquid state imperceptibly. Above 31 degrees Celsius, the isotherm is continuous, you can see here. The Andrews therefore concluded that if the temperature of carbon dioxide is above 31 degrees Celsius, it cannot be liquefied no matter how high the pressure may be. So therefore, he called this temperature 31 degrees Celsius as the critical temperature. So now, in these two parts of the video, we have discussed the lesson gaseous state. In the next coming video, we will discuss the next lesson liquid state. Thank you very much.